When a round is fired, gas is produced. This gas works on the bullet to push it to the desired range. This gas, which is following the bullet, is tapped at a particular point in the barrel and is used to work and operate the cycle of operations in the gas-operated weapons. The gas works on the piston head, which strikes the slide carrier, and it moves back, thereby unlocking the breech block and the moving parts. They also move back freely, thus carrying out extraction and ejection. Location of the gas vent. The location of the gas vent from where the gas is tapped from the barrel into the gas cylinder has to be such that, firstly, it should not affect ballistics, that is, there is no break in the pressure curve. Secondly, it should be after the all burned point, that is the ABP, so that the unburned particles of gas may not enter the gas cylinder and thus result in excessive fouling. To decide on the optimum location of the gas vent, let us consider all the advantages and the disadvantages of tapping gas near the muzzle end or the chamber end. Location of gas vent near the muzzle end. Once the gas vent is located near the muzzle end, low pressure gases will require a larger volume to be tapped to carry out the required task. The size of the gas vent will have to be thus big. Also, at the muzzle end, the gases start to resublime into solid carbon particles. This will cause excessive fouling and stoppages in the weapon. Once the gas vent is located close to the muzzle end, it will mean a longer piston and a longer cylinder. Which will increase the weight of the weapon. As a result of this, the delay involved in tapping of gas near the muzzle end, the rate of fire will also be much slower. Certain advantages are: tapping the gas near the muzzle end will ensure minimum effect on the ballistics of the bullet, because by then the gases would have already done the useful work in pushing the bullet and therefore will not affect the muzzle velocity. More delay involved, therefore the mechanical safety is easier to achieve. Also, the movement of the parts takes place once the bullet has left the barrel, as a result of which the weapon is considered to be much more accurate. Location of the gas vent near the chamber end. Once the gas vent is located near the chamber end, unburned gases will enter the cylinder. As a result, it will lead to excessive fouling. Also, the hot gases will erode the gas vent. As the gases will be tapped before they have done their useful work, it will affect the muzzle velocity and thus the ballistics of the weapon. Also, the gases coming into the cylinder will have high pressure. Therefore, the parts involved, that is the piston, the breech block and the carrier, must be made robust, and thus this will lead to an increase in the weight of the weapon. To make the weapon mechanically safe, a lot of delay mechanism will have to be incorporated to ensure the breech block does not unlock before safe pressure is achieved. This will lead to a complicated mechanical parts as also an increased weight of the parts. Once the gas vent is located close to the chamber end, the movement of parts will commence before the bullet has left the barrel. This will lead to a poor accuracy in the weapon. As the gases are tapped early, more will be the pressure acting on the piston head and therefore on the moving parts. Thus, the moving parts will move back at a faster rate. This will lead to a higher rate of fire in the weapon. Ideal location of gas vent. The location of the gas vent from where the gas is tapped from the barrel into the gas cylinder has to be such that, firstly, it should not affect the ballistics, that is, there is no break in the pressure curve. Secondly, it should be after the all burned point or the ABP, so that the unburned particles of gas do not enter the cylinder and thus result in excessive fouling. Mechanical safety. We have already seen in Auto Ops 1 as to how mechanical safety is achieved before firing in case of SLR and LMG. The other half of mechanical safety is achieved in a weapon by ensuring that the weapon is not unlocked before safe pressure is achieved in the chamber. The location of the gas vent is so made that it provides a certain amount of delay. This delay, which is provided, ensures that at the time of unlocking, a pressure of 2 tons per square inch or less has been achieved in the chamber. Control of op energy. Once the bullet is fired, tremendous amount of energy is produced in the form of gases. The gas available for tapping at the gas vent is having approximately 7 tons per square inch of pressure. To regulate this tremendous energy for performing the various actions involved in the cycle of operation, a gas regulator is provided. Presently, 3 types of gas regulators are available in gas operated weapons. They are the exhaust type gas regulator, the intake type gas regulator, and the constant volume gas regulator. The exhaust type of gas regulator has a constant volume of gas entering the gas vent. It is provided with different sizes of gas escape holes. Thus, the regulator varies the amount of gas that escapes through its gas escape holes, and in turn varies the amount of gas acting on the piston head to complete the cycle of operation. Variable intake type. In this type, the gas regulator is placed at the gas vent itself. Therefore, the amount of gas entering the cylinder from the barrel depends on the setting of the gas regulator. The bigger the number and the bigger the hole, therefore, more will be the gas entering the cylinder. An example of this is the gas regulator with the light machine gun. In this, we move the gas regulator from a smaller to a bigger number to increase the amount of gas entering the gas chamber. Constant volume gas regulator. In constant volume gas regulator, the gas enters a hollow piston and expands into the gas cylinder. In doing so, it forces the hollow piston against the operating rod, which is attached to the bolt. As it moves backward, the supply of gas to the hollow piston is cut off. The amount of gas which enters depends on the resistance to motion of the piston and the operating rod. Theoretically, as resistance increases, more gas is able to enter the piston so that there is more power available to operate the weapon. Piston. In gas-operated weapons, there is a need for a piston on which the gas acts, and which in turn acts on the carrier. Pistons are of 3 types: the short stroke piston, long stroke piston, and the direct gas action. Short stroke piston. In this type of piston, the gases act on the piston head, which in turn acts on the carrier. On completion of its work of imparting momentum to the moving part, it reverts to its original position with the help of a spring. This type of piston does tap action and normally does not move more than 3 inches. An example of this is the 7.62 mm self-loading rifle. Long stroke piston. In a long stroke piston, the gases act on the piston head, which in turn pushes the moving parts back. In this case, the piston is attached to the carrier or the slide and travels the entire distance back with the moving parts. This distance is generally more than 3 inches. An example of the same is the 7.62 mm light machine gun and the 5.56 mm INSAS rifle. Direct gas action. In the latest type of weapons, the piston has been entirely done away with. In direct gas action weapons, the gas, instead of acting on the piston, acts directly on the moving parts and pushes them back to complete the cycle of operation. An example of the same is the M16 rifle. Advantages of gas operated weapons. Flexibility in rate of fire. By regulating the intake of gas, the pressure acting on the moving parts can be regulated, and therefore the rate of fire of a gas operated weapon can also be regulated. Lightweight of the weapon. By optimum location of gas vent and the type of locking, the gas operated weapons can be made light in comparison to the recoil or the blowback operated weapons. Rate of fire. The cycle of operations in gas operated weapons begins simultaneously with the move of the bullet. Hence, a faster rate of fire is achieved in comparison to the recoil or the blowback operated weapons. Accuracy. In the case of gas operated weapons, once the round is fired, the moving parts in the weapon are minimum. This leads to increased accuracy of the weapon. Amount of energy. In gas operated weapons, the amount of energy tapped for completing the cycle of operation can be varied, thus making the weapon more versatile in its operation. Fumes. The gas operated weapons throw out fumes from the muzzle as well as the breech end after unlocking. This makes them unsuitable for enclosed spaces and armored fighting vehicles. Erosion. On the firing of the weapon, large amount of carbon particles stick to the inside of the barrel, as also the gas chamber and the piston head. Regular cleaning leads to erosion of these parts, thus affecting the functioning of the weapon. Carbon particles. The sublimed carbon particles get deposited in the gas vent and the gas regulator. The weapon, if not cleaned regularly, tends to develop large number of stoppages due to this gas fouling. Changing of barrel. Due to the complex design of the gas vent and the gas regulator, the changing of the barrel in gas operated weapons is relatively difficult as compared to the blowback or the recoil operated weapons. Blowback system of operation. When a round is fired, gas is produced. This gas acts on the cartridge case in all directions. In the frontal direction, it acts on the bullet. On the side, it acts on the walls of the cartridge case and expands it. And in the rearward direction, it acts on the base of the cartridge case, thus pushing it backwards. This gas energy action in the rearward direction is called blowback energy. Weapons which utilize this rearward thrust to complete their cycle of operation are classified as blowback operated weapons. Mechanical safety. To utilize the rearward energy, it is essential that the breech block supporting the cartridge case is not locked. This makes the weapon mechanically unsafe. However, in blowback operated weapons, mechanical safety is achieved by using a heavy breech block, a powerful return spring, parallel sided chamber and cartridge case, as also low powered ammunition. The heavy breech block and powerful return spring retard the rearward move of spent case and the breech block, thus providing the delay to ensure safe pressure is achieved in the barrel. The parallel-sided cartridge case and chamber increase the friction during extraction and in turn provide the delay to achieve safe pressure. Low-powered ammunition. The low-powered ammunition ensures minimum rearward thrust, thus providing mechanical safety. Simple blowback. In simple blowback, the bolt, often referred to as the breech block, is stationary at the instant of firing. The gas pressure forces the bullet and the bolt to move simultaneously. The inertia of the bolt, coming mainly from the mass, the stiffness of the return springs, and friction, are all that prevents the backward movement of the cartridge case from occurring too soon for safety. Delayed blowback. Delayed blowback allows for accurate single shot fire because the weapon using the system fires from a closed bolt. An example of the same is the German G3 rifle, which operates on the delayed blowback principle. When the round is fired, the gas pressure drives the bolt backwards and so forces the rollers into the main part of the bolt. The pressure by then is low enough for the empty case to be extracted safely. Blowback with API. In API, the round is fired when the round and the breech block are moving. The ignition is so timed that the round is fired just before the bolt reaches the limit of its forward travel. The energy produced during firing will have to do the following functions. Firstly, slow down and stop the forward movement of the breech block. Secondly, after the breech block comes to stationary position in the forward travel, to push it back to complete the cycle of operation. In this way, the total energy produced first has to bring the forward motion of breech block to rest and then push it back. Approximately 50% of breech block energy is used to stop forward motion of the breech block and the rest 50% is used to push it back. Therefore, by using blowback with API alone, we can reduce the weight of the breech block by half. An example of the same is the 9mm submachine carbine. Factors affecting the weight of the breech block and thus decreasing the weight of the weapon. Type of ammunition. If low powered ammunition is used, the gas generated on firing will also be less. Therefore, blowback pressure will be less. Thus, we can reduce the weight of the breech block. Length of the barrel. If the length of the barrel is reduced, the bullet will exit early. This will lead to safe pressure being achieved earlier and thus the delay or the retarding force to be that much less. As a result of this, the weight of the breech block, also the return spring, can be kept lighter. Return spring. The return spring, which is directly behind the breech block, and is applying some pressure on it is made stronger. Then we can to an extent reduce the weight of the breech block. Parallel sided chamber and cartridge case. If we use a parallel sided cartridge case and chamber, more portion of the cartridge case will come in contact with the chamber, thereby providing more friction during extraction. As a result of this, we can reduce the weight of the breech block. Blowback with API. In API, the round is fired when the round and the breech block are moving. The ignition is so timed that the round is fired just before the bolt reaches the limit of its forward travel. The energy produced during firing will have to do the following functions. Firstly, slow down and stop the forward movement of the breech block. Secondly, after the breech block comes to stationary position in the forward travel, to push it back to complete the cycle of operation. In this way, the total energy produced first has to bring the forward motion of breech block to rest and then push it back. Approximately 50% of breech block energy is used to stop forward motion of the breech block, and the rest 50% is used to push it back. Therefore, by using blowback with API alone, we can reduce the weight of the breech block by half. An example of the same is the 9mm submachine carbine. Dangers in advanced primer ignition. Early firing. Because of dirty ammunition or chamber, there will be increased friction during the two surfaces. During the chambering stage, the firing pin might strike the primer earlier. In doing so, the weaker portion of the cartridge case will be exposed outside the chamber and result in ruptured case. Hence, chamber and ammunition must always be clean. No firing due to excessive dirt. If there is excessive dirt in the chamber, then the forward motion of round will be stopped at the feeding stage itself, at which the round is not aligned to the firing pin. This will result in no firing. Hand chambering. When we hand chamber, we push the round into the chamber, thereby fully seating it. Weapons having blowback with API fire the round in forward motion. In this case, the firing pin strikes the primer when the round is fully ahead. Therefore, all of the blowback energy acts in the rearward direction. This will result in more recoil on the firer's shoulder and more wear and tear to the body of the weapon. So, the round has to be filled in the magazine before firing. Oversized round. Similar to the hand chambering is the case with oversized round. During its first move forward, the round is already seated in the chamber. Now, when the weapon is cocked and fired again, 100% of the blowback acts in the rearward direction. Also, if the round is more oversized, then burst can take place like in the case of early firing. Characteristics of blowback operation with advanced primer ignition. Bolt still moving forward when the round is fired. The heavy breech block is still in forward motion when the round is fired. The retarding force generated slows down the forward movement and pushes the breech block to carry out extraction. Unlocked breech. Before the firer presses the trigger, the bolt is positioned at the rear end. Once pressure is applied on the trigger, the bolt moves ahead under the pressure of the return spring. After this, the breech block is not locked, but fire takes place without locking. Heavy breech block. To absorb the rearward thrust and make blowback possible, the breech block is made heavier than the one used in gas or recoil operated weapons. Powerful return spring. to retard the rearward motion of the bolt so as to allow safe pressure to be achieved in the barrel. The recoil spring is made very strong. Parallel chamber and cartridge case. Parallel sided chamber and cartridge case ensure maximum friction during extraction. This delays the process and allows safe pressure to be achieved in the barrel. Simple design. Design of blowback operated weapons are kept relatively simple, and they comprise of a heavy breech block, a powerful return spring, and a firing mechanism. Poor accuracy. Blowback operated weapons are characterized by poor accuracy at long ranges. The movement of heavy breech block after pressing the trigger results in considerable shift in the CG, resulting in poor stability of the weapon during fire. Precision ammunition. Owing to parallel chamber, the ammunition is precision made. This leads to a lot of stoppages due to dirty chamber or unfit ammunition. Advantages of blowback operation. Simple design and working. As compared to gas operated weapons, the blowback operated weapons have a simple design and the working principle is also very simple. Cheap. Owing to the simple design of the weapon, the blowback weapons are very cheap to manufacture. Robust. The parts in blowback operated weapons per force have to be made stronger to take on the blowback force. Therefore, the weapon is also sturdy. Disadvantages of blowback operated weapons. Heavy breech block and heavy parts of the weapon. Hence, the total weapon is a heavier weapon compared to the gas or the recoil operated weapons. Inaccurate. Blowback operated weapons are characterized by poor accuracy at the long ranges. The movement of heavy bolt after pressing the trigger results in considerable shift in the CG, resulting in poor stability of the weapon during fire. Short effective range. Because of the use of low powered ammunition, as also the poor accuracy at long ranges, the blowback operated weapons have a considerably short effective range. No means of adjusting power. As in the case of gas operated weapons, the blowback operated weapons do not have any means to adjust the power. Fumes from the breech end. Because of the move of the breech block in a rearward direction before the atmospheric pressure is reached in the barrel, some gases enter the body of the weapon and fumes are formed at the firer's end. Recoil system of operation. As per Newton's third law of motion, every action has an equal and opposite reaction. When the bullet is fired, it moves forward. The move of the bullet in the barrel has an equal and opposite reaction on the breech face. As the breech face is locked with the weapon, the reaction is passed down to the weapon and automatically to the shoulder of the firer. As per the energy distribution, 1% of the total energy generated when a round is fired is the recoil energy. free floating barrel. To make the optimum use of the recoil energy, the barrel of the weapon is free floating. The bullets move through the barrel, and right up to the time it leaves the muzzle will have energy acting on the barrel, which will have an equal amount of energy acting backwards. If we have a fixed barrel, then the backward energy will go waste. Breech block. The breech block is locked with the barrel and travels the entire distance backwards with the barrel. Unlocking device. To carry out the complete cycle of operations, the breech block has to be unlocked with the barrel. This is done by a suitable unlocking device placed in the rearward path of the breech. Breech lock. After unlocking with the barrel, the breech block has to get locked at the back to ensure the barrel moves fully forward before firing the next round. Breech lock unlocking device. Once the barrel has reached fully forward, the breech block, which is locked at the rear end of the weapon, travels forward to feed, load, and fire the next round. For this, a suitable unlocking device is provided in recoil operated weapons. Outer casing and other parts. Recoil operated weapons are characterized by robust outer casing and other parts. This is to ensure that the weapon is strong enough to sustain the wear and tear caused due to recoil in the weapon. Long recoil. When the round is fired, because of the recoil energy, the breech block and the barrel move backwards. The breech block is locked to the barrel. When the breech block reaches the extreme limit of its rearward movement, it contacts the limiter, which locks the toggle joint lock. The limiter limits the move of the barrel in the rearward direction. The barrel becomes free or is unlocked to move back with the help of its spring. Now, extraction takes place. The breech block, on contacting the rear buffer, moves forward and gets locked up with the breech lock. Ejection takes place. The barrel moves forward to its original place and here presses on the breech unlocking device. The breech gets unlocked and starts moving forward. It takes the topmost round of the magazine, feeds it, loads it, and after the toggle joint gets pressed down and the breech block gets locked to the barrel, the weapon is mechanically safe for firing. The barrel does not travel the complete length backwards. It contacts the limiter as soon as safe pressure is achieved in the chamber. At this point, the barrel gets unlocked and moves back with the help of its spring. The breech block contains its movement backwards. The help of an accelerator is made, which is placed in between the barrel and breech block, and when the barrel gets unlocked and moves ahead, it moves in a pivotal motion and provides added acceleration to the breech block in the rearward direction. At the point of the limiter, when the barrel unlocks and moves forward, extraction and ejection takes place. The breech block, on reaching the limit of rearward motion, starts moving ahead, wherein it feeds, loads, and locks. Mechanical safety. To ensure the mechanical safety before firing, the breech block is locked to the barrel. To ensure mechanical safety after firing, that is, the weapon does not get unlocked till such time safe pressure is achieved, we ensure the barrel and the breech block remain locked till such time safe pressure is achieved in the chamber. At this time, it meets an unlocking mechanism which unlocks the breech and the barrel, and extraction, ejection, etc. takes place. Mechanical safety. To ensure the mechanical safety, before firing, the breech block is locked. Simple barrel change. Owing to the free floating barrel, the changing of a barrel of the recoil operated weapon is simpler than in gas or blowback operated weapons. Less fumes. As compared to gas operated weapons, the fumes coming out of the breech end are comparatively lesser. Suitable for armored fighting vehicles. Recoil operated weapons, because of their inherent advantage of a simple barrel change and less fumes, are more suitable in armored fighting vehicles. No fouling. Unlike gas operated weapons, wherein the gas travels through the gas chamber, fouling in recoil operated weapons is considerably lesser. Reliable weapon. Owing to less fouling, the stoppages in a recoil operated weapon are considerably lesser, hence, the weapon is much more reliable. Robust. All parts of the recoil operated weapon are made robust to take on the recoil energy. Slow rate of fire. Only 1% of the total energy is used as the recoil energy. Hence, the rate of fire achieved in recoil operated weapons is considerably lesser. No means of adjusting power. Unlike gas operated weapons, the recoil operated weapons do not have any means to adjust the power. Heavy parts. As the parts of the recoil operated weapon are made robust, the overall weapon is heavy. In this CBT, we've covered the weapons, firing the gas system of operation, the blowback system of operation, and the recoil system of operation. Having the knowledge of our weapon will enable us to use our weapons to optimum utilization, as also it will give us the ability to find faults with the present weapon system and to eliminate the same for the construction of new weapons.